Electricity. It's the lifeblood of our entire modern world, right? But have you ever stopped to think about how we actually control it? How do we tell it where to go, when to stop, and most importantly, which direction to flow? Well, we're going to dive right into that because the answer lies in a tiny, incredible component that acts as the ultimate gatekeeper. Okay, so to get a handle on control, you got to look at the two extremes first. On one side, you've got conductors, like the copper in your wiring. Think of them as a wide-open superhighway for electricity. They are always, always on. And on the other side, you've got insulators, like rubber. These things are like a solid brick wall. They are always off, totally blocking any flow.
But that's the big problem, isn't it? Our electronics are way more sophisticated than just on or off. We need nuance. We need precise control. We don't just need a switch. We need something more like a valve or a dimmer. So how in the world do you build that?
Well, this is where things get really interesting. The answer is in a very special class of materials that sits right in the middle of that spectrum. They're not always on, they're not always off, they're controllable. So let's meet the hero of our story today, the semiconductor.
A semiconductor, and the most famous one by far is silicon, is basically the Goldilocks of materials. It's not a great conductor, and it's not a great insulator. It's just right. And here's the kicker. Its ability to conduct electricity can be changed. It can be manipulated, precisely controlled. But how? The secret, it turns out, is something called the energy band gap. Okay, stay with me here. For an electron to conduct electricity, it has to jump from a lower energy level to a higher one. Think of the gap between these levels as a hurdle. In a conductor, there's basically no hurdle at all. Electrons just flow freely. In an insulator, that hurdle is massive, like a skyscraper. It's almost impossible to jump. But in a semiconductor, the hurdle is small. It's manageable. We can actually give electrons just enough of a push to get over it. And giving it that push comes from a process that is, for all intents and purposes, hacking the silicon itself. It's this incredibly clever recipe that turns a plain, middle-of-the-road material into a powerful electronic tool. And this process has a great name. It's called doping. Doping is just the intentional introduction of tiny, tiny amounts of specific impurities into a pure silicon crystal. It really is like adding a pinch of a special spice to a recipe. And by doing this, we can completely change silicon's electrical behavior and create two very different types of material that we're going to need. First up, let's make something called N-type material. We take our pure silicon and we sprinkle in a donor impurity, like phosphorus. Now here's the deal. Silicon atoms have 4 outer electrons to make bonds with. Phosphorus has 5. So 4 of those bond perfectly with the silicon. But that 5th electron is, well, it's a loner. It's left over with nowhere to go. It becomes a free electron, a ready-to-move negative charge. And that's why we call it N-type, for negative. Simple, right? So what's next? P-type material, of course. This time we use an acceptor impurity like boron, which only has 3 outer electrons. So when it tries to bond with its 4 silicon neighbors, it comes up 1 short. This creates an empty spot, a missing electron. We call this a hole, and here's the wild part. It behaves just like a positive charge. A nearby electron can jump into the hole, which just leaves a new hole behind. So it looks like this positive hole is actually moving through the material. And that's why we call it P-type, for positive. And there we have it. We've just made our 2 custom building blocks. We've got N-type silicon, which is flush with extra electrons. And we've got P-type silicon, which has all these extra positive holes. Each one is now primed and ready for action. But the real magic, the real magic, happens when we bring them together. So we've made our 2 custom materials. Now for the main event. What happens in that one microscopic moment when we join them? When P-type meets N-type? Because this right here, this is where our gatekeeper is born. The instant they touch, physics just takes over. That sea of free electrons on the N side looks across the border and sees all those empty holes on the P side, and they just can't resist. They rush across the boundary to fill them up. This frantic exchange, right at the junction, creates a neutral zone that's totally depleted of any free charge carriers. And we call it, fittingly, the depletion region. This whole process sets up a tiny but absolutely crucial electric field across that region, a built-in barrier. And for silicon, that barrier is super specific. It's about 0.7 volts. The best way to think about this is like the force you need to open a spring-loaded gate. Any electron that wants to cross this junction now has to pay a toll. It has to overcome this 0.7 volt barrier. Our gate is officially in place, so how do we open and close it?
We control the gate by applying an outside voltage, and this process is called biasing. And this, my friends, is what unlocks the diode's superpower, its incredible ability to create a one-way street for electricity. Here's exactly how we control that gate. In what's called forward bias, we connect the positive end of a battery to the P side and the negative end to the N side. This gives all the charges a big push toward the junction, shrinking that depletion region and easily overcoming the 0.7 volt barrier. The gate swings wide open, and current flows like a river. But if we flip the battery around, we put it in reverse bias. This yanks the charges away from the junction, making the depletion region wider and that barrier even stronger. The gate slams shut. No current allowed.
And that, right there, is the entire job of what we've just built, a PN Junction Diode. The source material puts it perfectly. It conducts current in one direction and offers high resistance in the other direction. It's an electronic one-way valve. It's that simple and that profound. So, a one-way street for electricity sounds pretty neat, but you might be wondering, why is that so ridiculously important? Well, let's look at one of the most fundamental jobs a diode does, a job that makes pretty much all of our modern electronics possible. Okay, here's the challenge. The power coming out of your wall socket is alternating current, or AC. The electricity literally flows back and forth 60 times a second. But your laptop, your phone, every gadget you own, they need direct current, or DC. That's a steady, stable flow in just one direction. We have to convert it. So we put our diode in the circuit. Now during the positive half of that AC wave, the voltage is positive. This puts our diode into forward bias. What happens? The gate opens, and that pulse of electricity is allowed to pass right on through. Easy. But then, the AC wave flips to its negative half. The voltage becomes negative. This instantly puts the diode into reverse bias. And what happens then? The gate slams shut. That entire negative half of the wave is completely, totally blocked. And what's the result? We've literally chopped off the entire backward flowing half of the current. We've turned a chaotic back and forth flow into a series of positive pulses. We've successfully rectified the current, creating the pulsating DC that, with just a little more smoothing, is ready to power our devices. And that's the power of the diode. A simple, unbelievably clever junction of two types of silicon that acts as the fundamental gatekeeper for electricity. It's truly the foundation of modern electronics. And it leaves us with this final, tantalizing thought. This simple, one-way gate absolutely changed the world. So what could we build if we made that gate even smarter? What if we could add a control knob to manage not just if the current